All right. So diversity is an excellent thing, but is there such a thing as too much diversity? Let's say, for example, you had students from 3 different institutions with 3 different projects who got together to form a RockSat team. Well, that is us. We are the Community Colleges of Colorado, a joint venture between Arapahoe Community College, the Community College of Aurora, and Red Rocks Community College. Now, these are our 3 mission statements, and we'll have our excellent team leads go over them in a second. But before that, I just want to talk about some of the mechanical aspects of our payload. So we are half canisters sharing with the Stevens Institute of Technology, and we use some rather interesting manufacturing methods for some of aspects of our payload. For example, we use CNC machining to create the base plate, to put the holes exactly where we want them to be, and to make extras so that if something wrong happened in testing, we wouldn't be out of luck. We also use a lot of 3D printing for various critical components, including the biology experiment, which Lev will talk about now.
All right, so for the biology experiment, we actually tested 2 different kinds of DNA. We used the plasmid DNA from an E. coli bacteria. Oh, wrong way, sorry. All right, and then we also used the calf thymus DNA, which is a nuclear DNA with a double helix shape, which you're more comfortable with or more familiar with. And then using the experiment, we tested the vibration and G-forces that the sounding rocket produces to simulate the fragility and the structure of the DNA. And I'll pass it on to Ms. Jamie.
A second component of our payload was a ring imaging Cherenkov radiation detector. This is a cosmic ray detector of our own design that we built out of a hacked GoPro camera. To hack the camera, what we did was we installed a small refractive medium, a little bit of magnesium fluoride, in front of the image sensor on the camera. What happens is when this camera is struck by a particle from a cosmic ray, the particle can move faster through the magnesium fluoride than light can pass through it. And consequently, what happens is something that is analogous to the sonic boom of light. We essentially get a little spark, a light cone that will emit from that particle's position. When that light cone hits our image sensor, we can take a picture of it and we get a little ring. And the geometric properties of that ring can tell us interesting things about the particle that we encountered, such as its velocity and its momentum. And with that, I'll pass it over to Philip to tell us about our other radiation experiment.
Okay, the final experiment on the payload is an experiment with carbon fiber shielding. It's a very simple and direct experiment. It consists of 2 Geiger counters, identical to RockOn, one of which the Mueller tube is encased in a block of carbon fiber. The purpose of this is to measure the decrease in radiation between our control and our shielded Geiger. Back to George.
So now I just want to go over some of the electronic aspects of our payload. On your right, you'll see a schematic of how everything is wired together. And just to talk about the flight computer for a second, we designed our flight code with 3 aspects in mind. First, we wanted it to be fast, logging quickly, so we have a lot of data to work with. And we got this, we're able to log about 3 times every 2 milliseconds. We also want it to be fault tolerant, because if for whatever reason something breaks on flight, we want everything else to work properly and give us good data. And finally, we wanted it to be easy to analyze at the end so that we can take everything, convert it to a CSV file into Excel, and easily analyze data and get some good conclusions out of it. So I just want to conclude with a couple of the lessons we learned from this, and there were many. But science by committee is a bad idea. It may seem diplomatic to take aspects of everybody's ideas and combine them into one experiment, but what you may end up getting is a Frankenstein project of sorts that doesn't accomplish much in the way of science, but it appeases people on the team. But it's important to recognize that this is happening, and don't fear de-scoping it, even if it means taking it out of the payload. We had a similar experience with this with a fluid flow experiment that ended up being scientifically rather useless. And we were lucky enough to recognize this soon enough, and we took it out of the payload, and we're a lot better from that. Now, the pi rule always applies. This states that it takes 3.14 times as long to do something as you think it's going to take. So budget accordingly. And documentation and presentation work, like we're doing now, is important to the presentation. It's not a distraction from the science, but it's part of the science itself. because you need to be able to share your findings with all you lovely people. And finally, RockSat was an incredible learning experience for us all, and we want to thank Space Grant and you guys for your attention.
And on the last note, I just wanted to say, do what you love, don't be afraid to explore the unknown, and rock on.
All right, thanks guys.